Now for part 6. Welcome back to Side A, Side B study of the inverse function and its characteristics with extra videos. Like this one, the definition of a radical as a rational exponent. Nice, but how does that have anything to do with inverse? For our case, taking the positive nth root of a number is the inverse operation of exponentiation.
How are we supposed to stay awake with no coffee?
My grandfather told me an old Oriental trick for staying awake if you had to. You convince yourself that if you fall asleep, you die. Thinking about it keeps you awake.
And it's a defining operation to conclude the last proof. So we want to prove the white box. To do that, we'll call on a new friend, the nth root of x, but this one has the definition of the radical with a variation. If you watched our previous video, recall the definition. The nth root of a number x is a number r such that r to the n equals x. Here the definition is slightly different. Just consider the first orange bullet. The nth root of a number x to the m is a number r such that r to the n equals x to the m. The definition of the radical logically follows with the last orange bullet. Instead of the nth root of x, which is r equals x raised to the power of 1 over n, rather the definition of the radical, the nth root of x to the m, which is the said number raised to the power of 1 over n, but written with the radical symbol that indicates the root of a number, which equals r. Essentially, the radical refers to the entire mathematical expression that uses the radical symbol to indicate a root. The number or expression, which is x to the m, under the radical symbol is called the radicand. M is the exponent of x, n is the index, which accommodates the type of root, such as cube root if n equals 3. If no index is shown, it's understood to be a square root, which means n equals 2. The operation returns the root, which equals r. In our case, we're considering the principal nth root. For example, the principal square root of 16 is the positive number 4 if x equals 16, n equals 2, and m equals 1. The principal square root of 16 cubed is the number 64 if x equals 16, n equals 2, and m equals 3. For convenience, we've tightened up both definitions as one phrase. Then in column 1, let r equal x to p over q for any positive integers p and q and any non-zero positive real number x. Next, raise both sides to the power of q, which returns the following definition, which we just discussed. In column 2, since r is the kth root of x to the p, by the definition of the blue box, r equals the kth root of x of p in radical form. To conclude the proof, use substitution. We have the kth root of x of p in rational form equal the kth root of x of p in radical form. Since n and m are also any integers, we are done. Next, like in the previous video, we want to show notation equivalence in the white box. We'll use established facts, such as the radical definition, blue box, the kth root of x, the yellow box, and what we just established, the red box. To start off, consider the first orange bullet. We want to show the two terms are algebraically equivalent. Then consider the second orange bullet. On the left-hand side, we have x to the p over q raised to the power of q, which just equals the right-hand side. The term in the brackets on the left-hand side rewritten using the power rule for exponents. We get x to the p raised to the power of 1 over q times. See that? In the second column, we do a series of rewrites. of the left-hand side, which returns x to the p. It looks a little crazy, but it's really not. All we're doing is rewriting the exponents. Let's unpack what we just did by expanding the notation for convenience. At the start, we want to show the two terms in the purple are algebraically equivalent. Next, the term in the brackets on the left-hand side is rewritten as the term on the right-hand side, q times. Then we do a series of rewrites of the left, which just equals x to the 1 over q to the p raised to the power of q. What we just said, rewritten 3 times to get x of p. We think, for us anyway, sometimes if the notation is bigger, it's more understandable. What do you think? Next, we rewrite the right-hand side. We just use the power rule of exponents to get the same, x to the p. Hopefully, by zooming in, the viewers can see the process better. What just happened? Take a look. The orange box is found in the left-hand series. The blue box is found in the right-hand series. As it turns out, they both equal to x of p. Thus, they equal each other algebraically by the definition of the kth root. Alright, getting back to the proof. Essentially, we use zoom to clarify the operations of column 1 and 2, right up to the second orange bullet in the second column. We can conclude the proof by combining the green and white boxes. Since both terms in the green box are equal to x of p, their kth roots must equal each other. Therefore, we have the white box. We are done. But let's unpack what we just said, because we have time and it's a walkthrough. Just consider what we just established. The following terms of the left side equal each other. Nice, because we can use the facts of the yellow and red boxes to rewrite both terms. So the term in the red box on the left equals the term on the right. The same can be said for the yellow box. The red goes with red, the yellow goes with yellow. See that? Now we just rewrite the first terms of the first orange bullet in radical form, the last orange bullet, by using established facts. So here's the scratch work of the logic. We have the right and left-hand side terms in the radical form. We have, if a equals b and a equals c, then b must equal c. We're using the transitive property, so it shows a and c are both equal to b, which means both are equal to x of p. Back to the proof. What do we know? The terms in the green box we labeled as a and c, respectively. Since both are equal to x of p, then their kth roots must also be equal. Recall, what does it mean to take the kth root? In previous examples, we called it the nth root. We raise each term in the green box to the power of 1 over q. Using the power rule returns the white box, therefore showing notation equivalence, which is just taking the inverse of exponentiation.
Look, you're all welcome to use the couch in my office. Anybody wants to take a nap?
Not me.
So everything, but just barely everything, is in the proof. But we thought clarifying the scratch work could be helpful for everyone, including for us.